Welcome to science class. Today, we are going to begin exploring the universe outside of our local neighborhood. In the near future, we will learn about stars and their properties, how they create elements, what happens when they die, including the formation of black holes and supernovae, the properties of galaxies, and the structure of the universe. But before we do that, we need to know how to study the universe. Astronomers use a wide range of tools to study the cosmos, but by far the most useful is the telescope. When you think of telescope, you probably think of this. But this is a telescope. So is this. So is this. An optical telescope gathers visible light data, but other telescopes collect infrared, radio waves, X-rays, and more. All of these things, visible light, infrared, X-rays, microwaves, these are all types of electromagnetic radiation. The James Webb Telescope, the literal and spiritual successor to the Hubble telescope, is incapable of taking regular pictures of anything. It can only take infrared images, which is invisible to us. Many videos ago, I said that astronomy is incredibly humbling. Astronomy teaches us that what we can see with the gift of sight is a tiny fraction of what's out there. Here are several images taken of the sun using different kinds of electromagnetic radiation. Here are several images taken of the Milky Way galaxy using different kinds of electromagnetic radiation. We could have never learned all that we currently know about the universe unless we developed technology to do what humans can't do. Let's get started. I'm about to turn your world upside down. Now, not like that. Light is not what you think it is. When you think of light, you probably think, well, that's illumination. That's what allows me to see. But that's visible light. The word light is basically interchangeable with electromagnetic radiation. So, what the heck is electromagnetic radiation then? Electromagnetic radiation is energy that travels in waves. These waves can travel through space because the energy of these waves moves through electric and magnetic fields, which are everywhere. That's why they're called electromagnetic waves. Let me grab something quick. The only difference between a C note and an E note is the frequency. The sound waves that make this C note have a shorter wavelength, so the pitch is higher. The only difference between the different kinds of electromagnetic waves is the frequency of the waves. Radio waves have wavelengths ranging from more than a kilometer wide to a millimeter wide. Microwaves are between 1 millimeter and 25 micrometers, infrared between 25 and 2.5 micrometers, and so on. Visible light is the part of the electromagnetic spectrum where the EM waves are between 380 and 700 nanometers. Gamma rays are up to 10 orders of magnitude smaller than visible light, or in other words, 10 billion times smaller. And a kilometer-wide radio wave is 2.5 billion times larger than a visible light wave. So again, the portion of the EM spectrum that we typically call light, visible light, is an insanely narrow part of the whole EM spectrum. If we stretched out the entire electromagnetic spectrum across the width of the United States, visible light would only be as wide as a dime on that spectrum. Once again, the only real difference between these kinds of waves is their wavelength, and therefore their energy as well. All electromagnetic waves travel through space at the speed of light, so their frequency is determined by their wavelength only. So for the record, when I say light, I mean the entire spectrum of electromagnetic radiation. If I'm talking about visible light, I will always attach visible to it, so you know exactly what I mean. We know what electromagnetic radiation is, so how do we use it? All objects in the universe emit some kind of electromagnetic waves. You don't glow, but you are warm. You emit infrared radiation. I could see you in the dark using an infrared camera. I could even see you from behind certain types of barriers with infrared. Certain materials are transparent to specific kinds of light, but opaque to others. Visible light travels through glass, but most types of infrared cannot, so you are invisible to infrared from behind an object that we regard as transparent. But infrared can penetrate things that visible light waves cannot. Infrared penetrates through smoke and clouds. Stars are incredibly bright, but even they can be covered by light years worth of space dust and debris. Here's a photo of the Carina Nebula in visible light and in infrared. Notice how we can see many more stars with the infrared image, because infrared passes through the material that visible light cannot. This is like trying to estimate the population of a city by only counting the people who you can see outside. Your number would obviously be way lower than the real population. By using many different kinds of electromagnetic radiation to study the universe, we learn more about what's really out there and how much of it there is, and more of its properties than visible light alone can tell us. Stars emit much more than just visible light. The heat you feel from the sun is from the infrared energy it outputs. Even though it is 150 million kilometers away, we still feel the heat. Most of the energy the sun puts out falls between wavelengths of infrared, visible light, and ultraviolet, but it does emit X-rays and gamma rays as well. What we find is that as an object gets hotter, the portion of the electromagnetic spectrum its energy emits shifts. This is why as you heat metals, they eventually glow. Visible light waves are more energetic than infrared. At first the metal just gets hot, but then as it gets even hotter, it starts to glow. And it glows red, then orange, then yellow, because red is the lowest energy wavelength of visible light. While our sun emits most of its energy in the infrared to UV range, a much larger star emits more of its total energy as a percentage higher up on the electromagnetic spectrum. EM radiation can also tell us what the universe is made of. We'll use sound as an analogy again. Different instruments have different sounds, so we can know what instrument produced a sound without being able to see it. As I stated before, all objects emit some kind of electromagnetic radiation, but not all objects emit the same kind of radiation in the same way. Hydrogen atoms emit energy differently than carbon atoms. Every single element has its own emission fingerprint, and spectroscopy is the science of studying those fingerprints. By using different kinds of telescopes, recording different kinds of EM radiation, we can look at objects in the universe and be able to tell what elements they contain. The whole universe is permeated with light. When that light strikes atoms, their electrons absorb some of that energy, but only at specific wavelengths. The specific wavelengths that are absorbed appear as dark lines on a visible light spectrum. Because every element is unique, the dark lines they produce is also unique. This is the fingerprint I alluded to earlier. In the 1920s, Cecilia Payne-Gaposchkin discovered using this technique that stars are composed almost entirely of hydrogen and helium. The conventional thought at the time was that the sun's composition was just like that of Earth's, only that the sun was incredibly hot, so it glowed. Later, we learned that almost the entire universe is composed of hydrogen and helium. Of all the matter in the whole universe, only about 2% of it is stuff other than hydrogen and helium. The final thing that EM radiation teaches us about the universe is that it is expanding. Once again, we will discuss sound for a comparison. You probably know about the Doppler effect. As a vehicle approaches you, the pitch it makes appears to increase, then decrease as it goes by. In reality, the sound coming from the object was always the same, but the waves of sound become compressed or expanded by the movement of the object. The same phenomenon happens with electromagnetic radiation. Let's look at the visible light spectrum for a second. As you move from left to right, the energy increases. So red light has the least energy and the longest wavelength, and blue light, we lump violet and blue together, has the most energy and the shortest wavelength. Let's say you had a blue light bulb. Then all of a sudden, that blue light bulb rushes away from you at an insane speed, say like 1% the speed of light. If you could watch the light bulb, what would you see? Apart from it getting smaller, its color would change. It would become red shifted. That doesn't mean it would necessarily look red. It just means that its color shifted towards the red end of the spectrum. It would appear perhaps green. But this is crucial. The light bulb itself doesn't change color. It's always blue. It just looks different from our perspective. If a red light bulb rushed towards you at the same speed, it would appear blue shifted. Again, it wouldn't necessarily look blue, it would just appear less red than it truly is. This will come up again in a later video, but when astronomers looked at the galaxies, they saw that basically every single one of them is red shifted. This means that the universe is expanding. And if the universe is expanding, that means at some point everything we see was condensed into a single point. That is what we will be learning about in the next video, the Big Bang. Thanks for watching.